Hey guys, welcome back to the channel. In today's video, we're going to be talking about a very interesting topic in computer science, which I recently came across. Now, the P versus NP problem is a very interesting problem in theoretical computer science, right? I'm sure some of you guys have heard about NP hard and NP complete problems, right? Everybody has some idea that NP complete problems are like basically impossible to solve or something like that. And I kind of wanted to talk a little bit more about this and hopefully give you guys a good explanation of what P versus NP is and why it's important. I give you guys like a short example of what this problem is about, right? So first of all, what does P mean? P stands for polynomial time, right? So what does that mean? Essentially, we represent the complexity of computer programs using big O notation, right? So let's say indexing through an array to find an element, right? So that is O of n, right? Or maybe sorting an array using bubble sort or insertion sort or something like that. That is O of n squared, right? Worst case. Or maybe you use like a divide and conquer approach to solve, to sort an array using merge sort or something like that. That would be O of n log n. Right. So essentially, we can represent the complexity of different algorithms in this format by using the big O notation. So, for example, searching, right? Sorting, etc. These are all polynomial functions, right? So it could be something like O of n squared, O of n log n, right? Something of this sort. So these are all polynomial functions, and we know that the solution takes at the worst case O of n squared or n log n, right? So in algorithms, we could have a problem statement, right? And the problem statement essentially says, you know what, we have an input, right? The input could be a data structure of some sort, right? It usually is. And then we run the algorithm, right? And then it gives us the output, right? Now the output could be a modified version of the data structure, for example, sorting, right? It changes the DS. Maybe it's checking if an element exists in an array or not. So it's like, does this exist? Or maybe you're given a graph, right? Does there exist? And you pick two vertices and you say that this is the node, and you know this is the source and that's the goal. So like, does there exist a path from source to goal, right? So in algorithms, in computer science, we call a solution a certificate, right? So a certificate is a solution to the problem, right? One solution which works, right? That might not be the output that you want, right? Your output may require you to find the total number of certificates or the most optimal certificate or something, right? But given a problem, a certificate is a valid set of, whatever. It's a valid set of constraints which satisfy the problem. Like, let's take the classic problem of denomination, coin denomination, right? Let's say I give you the number, let's say 555, right? And I tell you you have 10, you have coins worth 10, coins worth 5, and coins worth 1, right? What is the minimum number of coins with which you can make 555, right? Your answer would probably be 550 divided by 10, and the last 5 divided by 5, so it's like 56 or whatever. But I could change the coin values and the sum I need or whatever, but then what I'm asking you is to find the shortest combination of coins that gives you the sum, right? Now, that is one sum which has the shortest weight, right? But there could exist another certificate which satisfies the same problem, but you don't consider it because it is not the one that has the least number of points. For example, once again, if I had 555, the base problem is representing 555 as a combination of points of your denominations, right? So what I'm trying to tell you is that a certificate is a solution to the problem, right? For a sort, the certificate is the sorted array. It's simple, right? And for a search, it's simply the result. It's the answer that does this exist or not, or maybe you return the index of the search, right? The certificate is certificate is like a value. It's the index, right? The complexity of a solution, right? So let's say O of n or whatever, all these things I just mentioned here. Essentially, what we're doing is we are measuring the complexity of how long it takes to find the solution or to find a certificate, right? If you chose the base problem, then that is what it leads. You had no prior information or whatever, and how long does it take you to come up with a solution, right? Now, if I said that I'm giving you a certificate saying I'm giving you the solution, right? Check if this solution is correct, or check if this certificate is valid. Let's say the problem is search an array to find whether an element exists in the array or not, right? And I say yes, it exists, and it exists at index 10, let's say. Now what are you gonna do? To check the validity of the certificate, you're just gonna go to index 10 and see if that index has an element or not. That's it, right? So the solution took O of n to solve, because let's say O of n with a normal search and log n with a binary search, whatever, but I had to iterate through the whole thing to find the certificate. But to verify that the certificate works, you need O of 1 time. Just go in and check, right? If I gave you the answer and I said just check it, that's a lot easier than finding the answer yourself, isn't it? Right? This forms the basis of the P versus NP problem, right? So what is P versus NP? Okay, so I'm going to draw a large circle and I'm going to say this is P, right? What do I mean by P? I mean that inside inside this, I'm trying to draw like a set diagram, but inside this circle or this bubble or whatever lies all the problems whose certificates can be checked in a polynomial of n, right? Not the solution, but their certificates can be checked in a function of n squared, n4, whatever, O of n, right? Now, inside this, let's say, circle, there exists another circle called NP, right? So P means polynomial time, NP means non-deterministic polynomial time. Right? And what NP basically has is NP has a bunch of problems whose certificates can be validated in polynomial time, but whose solutions can only be validated or can only be found in exponential time. Which means that these problems are super hard to solve, but once you know the answer to the solution, it's not that hard, right? For example, if you had, let's say, a puzzle, right? I'm just gonna try and draw like a basic puzzle here. Maybe. I mean, assume this is like a basic puzzle piece, right? So now, if I gave you the pieces separately, without you know knowing what to place where, how you would solve the puzzle is you would have to place every piece. You have 4 orientations in which you can place the piece, like 4 rotations, right? So essentially you have 4 pieces here. So the number of ways you could place each piece, right? And the total number of combinations you have for this, you can already understand that it's 4 to the power 4, or for n pieces it's 4 to the power n. Why? Because while trying to find the solution, you could place each n piece in 4 orientations, trying to find the solution, right? So for n pieces, it's like 4 times 4 times 4 times 4 for each of the n pieces. So that's 4 to the power n, right? So it's an exponential time. It's very hard to solve the problem if you don't know, what fits where, like just mathematically, right? Because you're like trying everything. Now, if I gave you the solution, right? If I gave you the solution and I said that, here's the complete puzzle, right? Or here's what I think is the complete puzzle. Check if the puzzle is complete or not, right? All you need to do is go to a piece and check if that piece is connected to all of its neighbors or not, like properly connected, right? So if you had n pieces, the function would be like a value of a multiple of n, maybe like 4n or something, right? For each piece, one step is check up, check left, check down, check right. If everything is connected, great, move to the next one. Keep checking. If it's not connected somewhere, if something is missing, that means that the solution is not a valid certificate to the problem. The puzzle that you have given me is actually not complete, right? But if it is, if every piece is properly connected to all of the 4 pieces around it, you're good. The puzzle is fine, it makes sense, so you found the solution. But then this is a polynomial in n, and trying to find the actual solution from scratch is worst case exponential time, right? So this is an example of an NP problem, right? It's hard to solve, right? But if you have the solution, it's really easy to check if the solution works or not, right? So now we know what NP is, right? Now we have another, let's call it a circle or a subset in NP, and this subset is called NP complete, right? So what is NP complete, right? NP complete problems have a special characteristic, right? So NP complete is a set of NP problems, all of which have a very special feature, right? So it's like a special set of NP problems which have a feature, and the feature is all of the problems can actually be reduced to the same problem. Meaning, if you can solve one problem, or you know the way to solve one problem, you can actually solve all the other problems, right? What do I mean by this, right? So let's say the most basic problem, or the most let's say people call this like the king of all NP complete problems, or the most basic one is this problem called Boolean Satisfiability. Right? What does this mean? This is actually very simple. It just means that you have like x, right? Let's say you have variables x, y, and z, right? And the variables could have binary values, which means x can be 0 or 1, y can be 0 or 1, z can be 0 or 1, right? Now, let's say I simply give you I give you a statement, and the statement says x or y or z. That's it. And I say this is equal to 1. This is my, this is my expression, or this is the problem, right? Now, if you wanted a valid certificate to this problem, you need to plug in different values of x and y and check. I've given you a super obvious problem, so anything where x, and let's say I have 0, 0, 1, this works, right? 1, 0, 0, this works. So there can be so many certificates to this, right? And this, so now the total number of possible options you would have to explore to find a solution is 2 to the power n, where there are n variables. In our case, it's to the power 3 because there are 3 variables, right? That makes sense. From 0, 0, 0 to 1, 1, 1, binary, right? So now, this is like a super, like a super simple problem, but I could make like a big, convoluted kind of condition with like, x naught or y and z naught and y naught, something, whatever. And then if I make that equal to 1, it takes longer to find the solution. So essentially you're looking at 2 to the power n solutions where you have that many thing, right? So we can see that, or we know that the solution, we know that the solution to this problem is exponential time. It takes 2 to the power n, right? However, if we have the solution to this problem, meaning we have the values of x and y. It's really not that hard to get the solution. You just have to plug the things in and then compute the result. It's not that hard. So that can be done in, you know, a polynomial of n, right? Maybe it can be done easily, right? So this is an NP problem, right? But this problem is considered the king of all NP complete problems, or because every problem in NP complete can be reduced to this problem. So now if I gave you another problem, you might have run across, this is called circuit satisfiability, right? What does that mean? Well, it's the exact same thing as Boolean satisfiability, but instead of using the or and the ands, we're just gonna use like and gates, you know, and like or gates and stuff like that, you know, for like circuit logic or like whatever. If we do the same thing, it's the same thing. It's like, you know, whatever, we make some circuit and then they all connect, and then the output has to be 1 for like x, y, z, whatever, something else, like z, x bar, something. But it's essentially the exact same problem, just checking the answer, right? So circuit satisfiability can easily be reduced to Boolean satisfiability. Now let's look at something else, right? So another famous NP complete problem is the traveling salesman problem. Right. So what's the problem? The problem states that if you have 4 cities, right, or n cities, does there exist a path which hits every city once, right? You want one tour, and that tour must go through all the cities and must hit every city once, right? That's the problem, right? So now the traveling salesman problem can be reduced to the Boolean SAT, or the Boolean satisfiability problem, right? So how do we do this? Well, we can do this like in like a variety of ways, right? Essentially, like you could number like these nodes like 1, 2, say 1, 2, 3, 4. These are the numbers of your nodes, right? And let's say the path here is called 1, 2, the path here is called 2, 3, and the path here is called 3, 4, right? Let's say this path exists, it's called 1, 4. Let's say this path exists, it's called 2, 4, and whatever, right? So let's say 1, 2 is equal to 1. 2, 3 is equal to 1, but 1, 3 is equal to 0 because we don't have the other diagonal, right? So what you basically want is a sequence of these variables. You could assign the variables to the edges, and you want a sequence of them using like and or whatever, such that you get 1 at the end. You could like do a complicated, like, you know, check this and this and this, is that you get the same starting point, or like at least you get to the same point and everything else has been covered, or like whatever. I mean, you could do all that, and you could essentially reduce that to the same problem, which is Boolean satisfiability, right? So what I'm trying to get at here is every problem in NP complete can be reduced to the Boolean satisfiability problem, right? Every problem has an exponential time solution, and its solution can be verified in polynomial time, but it's a special case because they're all interconvertible, or they all can be converted back to the Boolean satisfiability problem, right? This is the circle of NP complete. Every problem is actually the same, or can be modified, or like, you know, transformed into the same problem, but you know, they appear as different problems, right? So Now you know what NP complete is, right? And you know what NP is. NP are, so this area right here, let's say the area right here, outside NP complete and inside NP are problems which cannot be converted into the Boolean satisfiability problem, but can have exponential time solutions and can be verified in time, like polynomial time, right? So now here's the thing, right? The question of what is P versus NP, if you look at this diagram, you know that P can both be solved and verified in polynomial time, right? And NP can be verified in polynomial time, but cannot be solved in polynomial time because, well, they're very difficult problems to solve, right? They couldn't be, they can't be solved in polynomial time. Now, here's where things get interesting, right? If you could prove P is equal to NP, you can prove that it kinda takes the same magnitude of time to find a solution and to verify that solution is correct. Okay, what I mean? Don't go into the nitty-gritties of what exactly the complexity of the verification and the complexity of the solution is, if they're differing in magnitudes of n. I'm just trying to compare between polynomial and exponential time, right? If you could somehow prove that P is equal to NP, you could then find solutions to the NP problems in polynomial time and then verify the solutions in polynomial time, right? Which you already can. But the basic question, or the basic, let's say, the topic of interest is, if you could prove this, finding the solution to a problem with no help whatsoever would be the same, would have the same level of difficulty, or would be as hard as checking whether a solution is correct, right? Now that makes no sense. Now, obviously, finding out the solution is going to be way harder than checking if a solution is correct, right? I guess there are some problems where I'm not really sure if there are any where both of them have the same complexity, but either way, if we could do them, we could kind of prove that they have they take the same amount of time, right? Which leads us to the crux of the matter, which is, you understand how ridiculous this is, right? There's a famous quote by, I forgot who, I'll leave a link in the description. I've forgotten who said it, but it was some, I think, famous theoretical computer scientist who said that if we could prove P was equal to NP, then every person who enjoyed music would be Mozart, and every person who was interested in investing would be Warren Buffett, right? You kind of get what I'm getting at here, right? Solving the problem is obviously way harder than checking if the solution is correct. But nevertheless, people are trying to find a way if this is possible or not, right? So this is like, theoretical computer science. And we're thinking in terms of algorithms and stuff like that, right? Algorithms is a thing where until a solution exists, you don't really know if it exists, right? You could think that a problem is super hard to solve until someone someday comes up with a method that's actually way easier. It could seem more complicated, but it actually does the same problem in a way faster amount of time, and your mind is just completely blown and it looks like magic to you, right? That is kind of what algorithms is like, right? Stuff like the one pass algorithm, or even essentially like basically dynamic programming. If you don't know what dynamic programming is, or if you don't know how powerful recursion can be, it can like simply blow your mind if you see how simple and elegant some of the solutions are. But nevertheless, a problem is impossible until it has been solved. If it has been solved, then it's done, right? You can't really know. And people are trying to prove this, right? People are trying to prove this because a lot of the problems that we see in a day-to-day basis is actually NP complete. A lot of the problems that we face in general when we go out and stuff, or like in the real world. For example, the traveling salesperson problem is, it's as simple as saying, it's kind of the same thing as finding the optimal path. Well, I mean, there are many of such problems which occur in like everyday stuff, right? What we do is, since we can't solve these problems effectively in polynomial time, we come up with approximate solutions which run in polynomial time, but give us, let's say, it's not the best solution, but it kind of works. Let's say it's let's say the error of the solution is within a threshold, but if you accept that level of error, you're able to find the solution in polynomial time, approximately, right? So that's kind of how I think navigation and pathfinding is a good example of this, where you could trade off the best path with a close enough path for time benefits, right? That's why people use heuristics and stuff like that in pathfinding. Anyways, the point is that several of the problems which we see on a day-to-day basis are actually NP complete. And if we were able to prove P equals NP, then that basically means we would be able to solve all these problems in NP in P time, right? Polynomial time. And this would massively change the world, because it would make engineering way easier, right? It would have tremendous benefits for stuff like molecular biology and, I don't know, protein synthesis, whatever, stuff like that. It would fundamentally, it would be like a scientific breakthrough in all fields of science if we could do this, right? It would be like gaining a superpower or something. It would change all fields of science, and it would radically change what is or what isn't possible, right? And that's why I think one organization has given a prize of like $1 million to the person who solves this problem. And it's not even about the money, actually. It's more about, I mean, it's such a famous problem that if you were able to solve this, you would potentially change the nature of like humankind forever in terms of advancements. But at the same time, if you look at the thing from a very logical standpoint, you kind of realize that it's actually not possible, right? I mean, there's no way that finding a solution to a problem, or every problem in NP, can be just as hard as checking whether a solution is correct. Like there's like no way, right? Or at least in terms of the complexity, the time, right? Hope you enjoyed this video on P versus NP. Leave a like, subscribe. Let me know down in the comments if you want to see videos about any more topics, and I might make some on them. And I'll see you guys in the next one. Okay, bye for now. Have a great day.